this is Ming. So our topic is a user matching pursuit method for metric factorization code stop problem. So first, before going straight to our core problem, we would like to give a quick review of the matrix factorization. So we have a user rating matrix R, and there's M user and N items. The goal of matrix factorization is to factorize the rating matrix into two lower rank matrix P transpose Q. So yeah. And this problem can be formulated as a well-known objective function as below, and where A is the user bias, and B is item bias, and mu is the average bias, and lambda controls the regularization terms. And actually, this is already a well-known literature and has been studied very intensely over the past year, and it's solved either by stochastic gradient method and coded descent. So here come our problem. So what if, like in the online recommendation system, there is a user, a bunch of users stream in daily. So we want to quickly predict the user's rating without retraining all the metrics of P. So for example, there's a new user stream come in up with partially observed rating are new, and we want to quickly know how to predict the rest of the rating for that users. So this is our problem we want to tackle.
So we start from a naive idea that the rating of the new user is protected through the feature vector of the new user. It's a linear system of the feature vector of the new user and the original Q. And P and Q is originally trained with the users we have. And so the optimization function can be formed like this. While W is the indicator function that says whether a rating is rated or not. And the time complexity is proportional to the iteration and the number of new users. And K is the number of Latin features, and N is the number of items. And the assumption is that the new user won't affect the original P matrix and the Q matrix, since they don't have a lot of ratings.
And another related word is that very similar to the previous ones. They obtain the P new user matrix in a similar way, but they incorporate the arrow term into the item matrix, and they use matrix sketching technique to obtain a lower dimensional matrix Q. And they use this Q new updated item matrix and then further update the user matrix P1, and they iterate through whenever their new user came in. So the time complexity mainly consists of two parts. The way how they use stochastic gradient to obtain the user matrix P new, and the time complexity of how they obtain the matrix sketching technique.
Okay, so next I will introduce our method. And the assumption of our method is that we think that the behavior of a user is a combination of a behavior of a few basis users. And so this assumption can model by representing the user vectors as a linear combination of some basis vector. And the coefficient of the combination should be sparse. And so suppose now we have T basis vectors for new users, and instead of directly estimate the user vector PU, we estimate the combination W, and so that is we try to match the new users with our basis users, and the combination can be obtained by solving the following arithmetic problem. So now you see the first line here we try to match the rating, and the second line we try to induce a sparsity on our combination coefficient by adding one regulator term, and the prediction time complexity is about the number of iteration times, the number of new ratings, and times of the number of bases. And so the next question is how to obtain those bases. And so we further factorize P into the D, which is the matrix composed by the basis vectors, and W. And so the optimization is look like this, the top one. So the first line is what we try to minimize the difference between the ratings and the prediction. And the second line is we try to revise our model, and also we add one return to induce the sporosity on the combination. So a nice property about this problem is that each single variable subproblems has a closed form solution, and so we solve these problems by covariant descent. And the overall time complexity is just a factor t more than a normal factorized max factorization problem solved by covariant descent. And next, we'll move on to the experiment part.
So this is our data set. There's around 6,000 users and 3,000 items, and the total ratings is around 1 million. And the number of Latin feature we're all using is 20. And so we split the data set into 90% training and 10% testing. And our task is, in the test set, given ratings of the partial ratings of the new user, and we predict the future ratings. So we evaluate it in two parts, the prediction time and the root mean square error. And the root mean square error is separated into two parts. One is the percentage, and one is the number of ratings. So for this graph, the red line is our proposed method, and the other line are the others. And x-axis is the percentage of known ratings. So for example, if we've 20%, so we use 20% of the known ratings for training, and we predict the ratings of the new user with this 20%, and we evaluate that with the 80%. So this increases with the percentage. And our method performs better than the state-of-the-art. And for this graph, the x-axis is the number of known ratings. So the number means that, so given one rating for a user, we predict the rest. If there's 100 ratings, we use one rating to predict the 99 ratings. And so our method generally performs